Solid earthquake geophysics is a field within geophysics focused on understanding the physical processes and properties of earthquakes. This branch of science plays a dynamic role in predicting seismic events, mitigating their impacts, and enhancing our knowledge of Earth's internal structure. By studying the interaction between tectonic plates and the resulting seismic activity, researchers can develop models that help in earthquake forecasting and hazard assessment. At its core, an earthquake is the result of a sudden release of energy in the Earth's crust that creates seismic waves. This energy release typically occurs due to the movement of tectonic plates. The Earth's lithosphere is divided into several large and small tectonic plates that float on the more fluid asthenosphere. The interaction at the boundaries of these plates, convergent, divergent, and transform boundaries, are primary sites of earthquake activity. Convergent boundaries. Here, plates move towards each other, and one plate is often forced beneath another in process known as subduction. This can lead to powerful earthquakes, often deep within the Earth's crust. Divergent boundaries. Plates move apart, allowing magma to rise from the below the Earth's surface and create new crust. Earthquakes at these boundaries are generally less intense, but can still cause significant damage. Transform boundaries. Plates slide past each other horizontally. The friction and the stress accumulation at these boundaries can result in significant earthquakes when the stress is released. Seismic waves generated by earthquakes are divided into body waves and surface waves. P waves, which is primary wave, are compressional waves that travel faster and are the first to be detected by seismograph. S wave, secondary waves follow, moving material perpendicular to the wave direction. Surface waves travel along the Earth's surface and often cause the most damage due to their high amplitude and longer duration. To measure earthquakes, scientists use instruments called seismometers. These devices record the motion of the ground and allow for the determination of an earthquake's epicenter, depth, and magnitude. The magnitude is commonly measured on the Richter scale or the moment magnitude scale. Predicting earthquakes remain one of the most challenging aspects of solid earthquake geophysics. While short-term prediction is currently beyond our capabilities, long-term forecasting based on historical seismic activity, geological studies, and plate tectonics provides valuable information for assessing earthquake risk. Mitigation plans involve both structural and non-structural measures. Building codes and construction practices are designed to enhance the resilience of structures, particularly in earthquakes-prone areas. Early warning system, public education, and emergency awareness plan are also crucial in reducing the impact of earthquakes. Recent advancement in technology and data analysis are pushing the boundaries of earthquake geophysics. High-resolution satellites imagery, GPS, and remote sensing technology provide detailed observation on crustal deformation. Machine learning algorithms are being developed to analyze a vast amount of seismic data, potentially improving the accuracy of earthquake forecasts. Moreover, deep drilling projects and the installation of dense seismic networks offer insights into the conditions within fault zone, helping scientists understand the triggers of seismic events better. These efforts contribute to building more robust model of earthquake processes and improving hazard assessment and the strategies that needed in this case. Solid earthquake geophysics is essential for understanding the complex of seismic phenomena and reducing and disturbing impact of earthquakes. While predicting the exact time of earthquakes remain unknown, advancements in this field are continually enhancing our ability to forecast risk and prepare for these natural events. As research develops, the integrating of cutting-edge technology and innovation methodologies promises to deepen our understanding of the Earth's dynamic processes and support our resilience against future seismic hazards.